In this video, we're going to talk about how to solve problems with exponential equations. Remember that we talked about these logarithmic properties in a previous lesson. You can use the properties of logarithms to rewrite and simplify log expressions. So for example, let's rewrite and simplify this expression right here, the natural log of e squared. So we can use the power property to rewrite this, right? We can bring that 2 down in front, so we have 2 natural log of e. So remember, if we're taking the natural log of something that is equal to the base, that is just going to equal 1. So this is basically 2 times 1, which will simplify to just 2. Now we have the log of 20. We can actually rewrite the log of 20 using the product property. Remember that this is basically the log of 2 times 10. So this is going to equal the log of 2 plus the log of 10. So remember, this log of 10, that is a situation where we have a base and we're taking the log of the number that equals the base. So we can just go ahead and turn that into 1. So this is going to equal the log of 2 plus 1. Now let's rewrite and simplify the natural log of e over 4. So we can use the quotient property to rewrite this as the natural log of e minus the natural log of 4. Well, the natural log of e, once again, we're taking the log of the base, so that's going to equal 1. So we have 1 minus the natural log of 4. So that is going to be the simplified form of this expression. So exponential equations, like the ones we've been talking about, actually have many applications. So let's look at some of those. One application is when we're talking about radioactive decay. So remember, in radioactive decay, every radioactive substance will lose particles or energy from the nucleus. As a result, radioactive elements change from one type of atom to another over time, which is a process called radioactive decay. So half-life is a common measurement for a radioactive substance. The half-life of a radioactive substance is the length of time it takes for 1/2 of the substance to decay. So we can use this formula to figure out how to solve problems involving radioactive decay. It tells us that A equals A naught 1/2 to the T over H power, where A naught is the initial amount of the substance, T is the time it takes for A of the substance to remain, and then H is the length of the half-life of the substance. Okay, so here's our formula. And what we're going to do now is we're going to look at an example. So it says carbon-14 has a half-life of 5,730 years. They find a bone that has 15% of normal carbon-14 levels. Determine how old the bone is to the nearest tenth of a year. So we know that we have 15% of the normal levels, right? So we can say that A equals 15% of A naught, right? 15% of the initial amount. So that is the same thing. If we change that to a decimal, that's saying that A equals 0.15 A naught. And we also have the value of the half-life, right? So that tells us that H equals 5730. So now we can go plug into our equation. So we have 0.15 A naught equals A naught times 1/2, and then that's T over 5730. So when we're solving this problem, I like to go ahead and just change that 1/2 into a 0.5. So we have 0.15 A naught equals A naught times 0.5 to the T over 5730. So now notice that we have an A naught on both sides, so that'll cancel out. So we have 0.15 equals 0.5 to the T over 5730. So now that we have a variable in the exponent, I'm going to go ahead and I'm going to take the log of both sides. So when I take the log of both sides, I get the log of 0.15 equals the log of 0.5 to the T over 5730. So I'm going to use that power property to bring this power down in front. So I have the log of 0.15 equals T over 5730 log of 0.5. Okay, so now I need to solve this for T. So I'm going to start off by multiplying both sides by 5730 to get that out of the denominator. So I have 5730 log of 0.15 equals, here this cancels, and I have T log of 0.5. So now to get T by itself, all I need to do is divide both sides by the log of 0.5. So when I do that, I get 5730 log of 0.15 over the log of 0.5 equals, and then here these two cancel, so I have that equals t. So that is my exact answer, but I can get an approximate answer using my calculator, right? I'm going to type this all in. So I do 5730 log of 0.15 and then hit enter and divided by the log of 0.5. And that tells me that it has been 15,682.8 years. Because in the original problem, it did want us to round to the nearest tenth, so we're just going to leave that rounded like that. So that is our answer. So here's another example of how we can use exponential equations in real life. So it says that Newton's law of cooling states that for a cooling substance with an initial temperature T naught, the temperature T of T after T minutes can be modeled by the equation T of T equals T of S plus T naught minus Ts e to the negative KT, where Ts is the surrounding temperature and K is the substance's cooling rate. A liquid substance is heated to 70 degrees Celsius. Upon removing it from heat, it cools to 60 degrees in 10 minutes. If the surrounding air temperature is 50 degrees Celsius, what is the substance's cooling rate? Okay, so a lot of information here. So we have initial temperature T naught, temperature T of T after T minutes, and we have this equation, and Ts is the surrounding temperature. Okay, K is the cooling rate. So it's asking us for the cooling rate, so we already know that we need to find K in this equation, right? So we have T of T equals Ts plus T naught minus Ts e to the negative KT. So when I have an equation like this with a lot of variables, I like to go ahead and label what I have based on the variables that are in the problem. So K we already know is our unknown, and we have all these other variables here. So it says T of T, which is the temperature after T minutes, okay? Well, it says upon removing it cools to 60 degrees in 10 minutes, okay? So we can basically think about that as like T of 10 equals 60 degrees. Okay, Ts is the surrounding temperature. Well, it tells us that the surrounding air temperature is 50 degrees Celsius. So Ts is going to be 50. T naught is the initial temperature, right? So it says it's heated to 70. So that's our starting point. So we have T naught is 70. And then T is how many minutes, right? So we already know that's going to be 10 minutes. So all we need to do is plug these numbers now into our formula. So we have 60 equals Ts, which is 50, plus T naught, which is 70, minus Ts, which is 50, e to the negative K, right? K is an unknown because we're trying to find it, so times 10. So we have 60 equals 50 plus 70 minus 50 is 20, so we have 20 e to the negative 10K. So now we're going to work on solving for K. So we're going to isolate that term that has the variable, right? So I'm going to start off by subtracting 50 from both sides. So that gives me 60 minus 50, which is 10. And then I have 10 equals 20 e to the negative 10K. All right, so I'm going to divide both sides by 20 to work on getting that variable by itself. 10 divided by 20 is 0.5. So I have 0.5 equals e to the negative 10K. So now let's work on solving this. So since I have an e, I'm going to take the natural log of both sides. So that gives me the natural log of 0.5 equals the natural log of e to the negative 10K. So I'm going to bring this power down in front. So I have the natural log of 0.5 equals negative 10K natural log of e. Well, that natural log of e is just going to turn into 1. So I have the ln of 0.5 equals negative 10K. Now to solve for K, all I need to do is divide both sides by negative 10. So now what I just need to do is I do the natural log of 0.5, hit enter, and then divide by negative 10. So when you do that, you will get 0.0693, and this is a rate of cooling, right? So it's going to be degrees Celsius per minute as our units equals the value of K. So that is the cooling rate of this substance. So remember that exponential equations can be used to solve problems involving many real-life situations.